What if the most dangerous fighter jet in the world was never limited by speed, stealth, or firepower, but by something far less dramatic? Not an enemy weapon, not a technological failure, just distance. Somewhere inside secure facilities across the United States, engineers have spent years solving a problem that few people outside military circles ever discussed. Now, the result is beginning to emerge into public view, and it may reshape the balance of air power for decades. At the center of the story stands a familiar aircraft, the F-22 Raptor. But the aircraft now taking shape is no longer the same machine that first entered service more than 20 years ago. When the F-22 Raptor entered the skies in 2005, it quickly became surrounded by an almost mythical reputation. Pilots admired it, rivals feared it, and military analysts struggled to find a true competitor. It could fly at extraordinary speeds, evade radar detection, and dominate air-to-air combat in ways that seemed almost unfair. For years, the aircraft represented the pinnacle of American aerospace engineering, a symbol of technological superiority that few nations could challenge. To the public, it appeared nearly perfect. Yet military history is filled with examples of powerful weapons constrained by unexpected realities. The F-22 was designed during a different era, when American strategic planning focused heavily on regions where friendly airbases were relatively close to potential battlefields. Europe and the Middle East shaped many assumptions behind its development. In those environments, range was important, but it was not the defining factor. The aircraft could launch, complete its mission, and return with support available nearby. Then the strategic landscape began to shift. Attention increasingly turned toward the vast expanse of the Pacific. Distances that looked manageable on a map suddenly became enormous when measured in operational realities. Airfields were separated by oceans, supply lines stretched across thousands of miles, and every mission demanded far greater endurance. An aircraft that could dominate an aerial battle still needed a way to reach that battle in the first place. For years, many observers assumed America's most advanced fighter already possessed every capability it would ever need. The narrative was simple. The F-22 was unbeatable, and therefore no major changes were necessary. Behind closed doors, however, military planners understood something very different. A fighter that depended heavily on aerial refueling could face serious challenges in a future conflict against a technologically sophisticated adversary. Tanker aircraft were invaluable, but they were also vulnerable. They were large, visible, and difficult to protect in highly contested airspace. Inside conference rooms at the U.S. Air Force, discussions increasingly centered on one question. How could the F-22 maintain its stealth advantages while operating much farther from support assets? Solving that puzzle would require more than a routine upgrade. It would require rethinking assumptions that had existed since the aircraft's birth. Engineers at Lockheed Martin began exploring possibilities that once seemed contradictory. More fuel usually meant greater visibility. Greater range often came at the expense of stealth. Yet the future demanded both. The answer emerged slowly through years of design work, testing, and refinement. Rather than treating external fuel tanks as an unavoidable compromise, engineers approached them as part of the aircraft itself. New low-drag fuel tanks were developed with shapes designed to complement the Raptor's stealth characteristics. Instead of creating obvious radar reflections, these structures were engineered to minimize their impact on the aircraft's signature. What sounded impossible on paper gradually became a practical reality. The significance of that achievement extends beyond engineering elegance. Additional range changes how commanders think. It changes where aircraft can operate, how long they can remain on station, and which targets they can reach. Suddenly, missions that once required complicated support networks become far more flexible. The aircraft gains freedom of movement, and freedom of movement often translates directly into strategic advantage. Imagine a future crisis unfolding across the Indo-Pacific region. Hundreds of miles of open ocean separate friendly bases from contested areas. Radar stations scan the horizon. Naval fleets maneuver cautiously through narrow maritime corridors. In previous years, planners would have calculated tanker routes alongside fighter operations, knowing that every mission depended on a carefully coordinated chain of support. With an extended-range F-22, those calculations begin to change. But range was only one piece of a much larger transformation. Even as engineers worked on fuel solutions, another challenge was becoming increasingly important. Stealth technology had spread. The United States was no longer the only nation operating low-observable combat aircraft. China's J-20 and Russia's Su-57 represented efforts to challenge traditional assumptions about air superiority. The question was no longer how to detect conventional fighters. The question was how to find aircraft specifically designed not to be found. For decades, radar served as the primary tool of aerial detection. It was reliable, proven, and deeply integrated into modern warfare. Yet stealth technology complicated that equation. Aircraft could be shaped to reduce reflections and coated with materials intended to absorb radar energy. Detection became more difficult, engagement timelines became shorter, and uncertainty increased. The battlefield was changing. Inside laboratories and testing facilities, attention shifted toward a different approach. Instead of searching for reflected radio waves, what if aircraft searched for heat? Every jet engine generates enormous thermal energy. No matter how sophisticated an aircraft becomes, physics imposes certain limits. High-performance engines create heat, friction produces heat, and movement through the atmosphere leaves traces. Unlike radar emissions, these signatures cannot simply be switched off. The result was the integration of infrared search and track technology, often known as IRST. On the surface, the concept sounds straightforward. In practice, it represents a profound shift in how combat aircraft gather information. Rather than broadcasting signals and waiting for responses, the system simply observes. It watches silently. It listens without speaking. Picture two stealth fighters moving through the darkness at high altitude. Neither wants to reveal its position. Neither wants to activate systems that might betray its presence. One aircraft suddenly begins collecting thermal data, quietly building a picture of the environment around it. The other pilot remains unaware. No warning lights flash. No radar alerts sound. The hunt has already begun. This capability alters more than individual engagements. It changes how formations operate. Aircraft equipped with advanced sensors can share information with other members of the group, creating a collective awareness that extends beyond the perspective of any single pilot. What one aircraft sees can benefit many. The formation becomes less a collection of individual fighters and more a connected network moving through the sky. As these developments progressed, additional improvements quietly joined the program. Defensive systems evolved. Electronic warfare capabilities expanded. Sensors became more capable and more integrated. Each enhancement reinforced the others, creating a layered approach rather than a collection of isolated upgrades. Engineers were not simply improving components. They were reshaping how the aircraft functioned as an entire combat system. Meanwhile, another limitation from the Raptor's early years continued attracting attention. Many modern fighters had adopted helmet-mounted displays that allowed pilots to access targeting information simply by looking toward a threat. The F-22, despite all its sophistication, had entered service without such a system. It was one of those unusual gaps that seemed increasingly out of place as technology advanced. The introduction of a helmet-mounted display changes the relationship between pilot and aircraft. Information becomes more immediate. Situational awareness expands. During high-speed engagements where seconds matter, reducing the distance between observation and action can provide a critical advantage. The pilot no longer feels separated from the aircraft's sensors. Instead, the aircraft becomes an extension of the pilot's perception. Far from public attention, another revolution was unfolding at the same time. Military planners were looking beyond individual aircraft altogether. The future of air combat increasingly involved collaboration between manned fighters and autonomous systems. Drones were becoming more capable, more intelligent, and more valuable in dangerous environments. Rather than replacing pilots, they offered ways to extend reach and distribute risk. The MQ-20 Avenger emerged as part of that broader vision. Unmanned, adaptable, and capable of supporting complex operations, it represented a glimpse of what future battlefields might look like. Integrating such systems with the F-22 opened new possibilities. A single pilot could influence events across a much larger area, coordinating assets that operated as a team rather than isolated platforms. Imagine a Raptor flying deep inside contested airspace. Around it, autonomous systems gather information, conduct reconnaissance, and position themselves for potential missions. The pilot is no longer responsible solely for one aircraft. Instead, that pilot becomes the center of a broader network. Decisions ripple outward through connected systems operating across the battlespace. At first glance, these developments might appear unrelated. Longer range, passive detection, enhanced defensive systems, drone integration, helmet-mounted displays. Yet viewed together, a different picture emerges. Each improvement addresses a specific challenge associated with future conflict. Distance, survivability, information dominance, force multiplication. The individual pieces form part of a larger strategic puzzle. The geopolitical context makes that puzzle impossible to ignore. Competition among major powers is increasingly defined by technology, industrial capacity, and the ability to adapt. China continues investing heavily in advanced aerospace programs. Russia pursues modernization efforts despite economic and operational challenges. Across the globe, nations are examining lessons from recent conflicts and preparing for uncertain futures. Against that backdrop, maintaining air superiority requires more than preserving existing advantages. It requires anticipating future threats before they fully emerge. That philosophy explains why resources continue flowing toward programs that may seem incremental on the surface but carry enormous strategic implications beneath. The objective is not merely keeping pace. It is staying ahead. Then comes the twist that changes how the entire story is understood. Many people assume these upgrades exist simply to extend the life of an aging fighter. They see modernization as maintenance, a bridge until something newer arrives. But the deeper reality is far more significant. The transformation of the F-22 is not happening in isolation. It is part of a deliberate transition toward a new era of air warfare. In 2025, attention shifted toward the next-generation air dominance program and the future aircraft known as the F-47. Public discussions focused on sixth-generation technologies, revolutionary capabilities, and the next chapter of American air power. It would have been easy to view the F-22 as yesterday's platform awaiting replacement. Yet, the modernization effort tells a different story. The Raptor is being positioned as a critical link between generations. Rather than fading into irrelevance, it is evolving into a bridge connecting established capabilities with future concepts. The technologies being integrated today help prepare pilots, commanders, and operational doctrines for the systems that will define tomorrow's battlefield. In that sense, the upgrades are about far more than extending service life. What appears to be an aircraft modernization program is also a strategic rehearsal. It allows the U.S. Air Force to experiment with networked warfare, autonomous collaboration, advanced sensing, and distributed operations using a platform that already possesses extraordinary combat credibility. Lessons learned today can shape decisions for decades. That realization changes the meaning of everything that came before. The extended range is not just about fuel. The passive sensors are not just about finding targets. The drone integration is not just about adding capability. Together, they represent a shift toward a new model of air combat where information, connectivity, and adaptability become as important as speed and maneuverability. As the sun sets over remote test ranges and aircraft disappear into the horizon, the transformation continues largely out of public view. Engineers review data, pilots evaluate systems, technicians refine components. Most of the work happens far from headlines. Yet history often turns on developments that attract little attention until their consequences become impossible to ignore. The F-22 Raptor once symbolized a revolution in air superiority. Now it stands at the threshold of another, not because it is being replaced, but because it is being reimagined. The aircraft that once dominated the skies through stealth and performance alone is becoming part of a much larger ecosystem, one designed for a world where battles are fought across vast distances and decisions travel faster than missiles. Years from now, historians may look back on this period not as the final chapter of the F-22 story, but as the moment it found a new purpose. A bridge between generations, a testbed for emerging concepts, a guardian of air superiority during a time of rapid technological change. And perhaps that is the most remarkable part of all, because the rail story was never about a fuel tank, a sensor pod, or a helmet display. It was about adaptation, about recognizing that even the most successful machine must evolve when the world around it changes. In the endless contest between innovation and obsolescence, survival belongs to those willing to transform before they are forced to. High above the clouds, where nations measure power in seconds and miles, that lesson may prove more important than any single aircraft ever built.